This is, I think I'm going to call it the Harmony Analyzer, and it's a Raspberry Pi Pico microcontroller running some C++ code, and there's a button and a microphone module, and this microphone module has a preamp built into it, which is really cool because it's a really tiny circuit board. And then there's this 32 by 8 display, and the idea behind this essentially is, it's a music visualizer, but it's supposed to be a music visualizer that could actually be useful in a jam session. So it kind of gives you information about what's being played. And this is one of my favorite modes because it's really simple in the way it works, but the effect is nice. So I made a video. Wait, I'll have to scroll through modes here. I'll talk about what these different modes are later, but here we go. So I made a video where I essentially made a version of this that runs on Windows console. And when I saw this screen on Amazon, the Max 2719 controlled 32 by 8 LED matrix, when I saw that on Amazon, I realized that if I could get my code to run on that, it would be a really cool as a guitar pedal, so that I could always kind of know what notes are happening in the music. And then what I realized is I had to kind of define the function to plot a histogram. And what I realized is I could actually put any kind of thing in each column for each value between 1 and 8, right? So if I then skip over to this mode, what I'm just doing is I'm not discriminating between 6, 7, and 8. And they're all just piano keys, and then anything lower than that is plotted on the top. And so you get this cool effect here, which is kind of would tell you what notes to play on a piano. And then this mode, okay, so this says bass, and what it's doing, I'm getting my guitar. This mode looks for power chords, so it looks for root fifth kind of thing. And so it kind of, if you play a major chord, it's going to detect the power chord within the major chord and give you the root note. And if you play a minor chord, it's going to do the same thing. And so this kind of tells you bass notes in some way. And then the next mode looks for triads. So it actually sometimes has trouble with open position chords because they have a lot of the overtones from just the way that works on guitar. But if you play bar chords, it more often gets the chord quality right. And then the next mode says chord, and this has chords with 4 notes in it as well, like this thing. So that's what that does. And then there's this mode, which I kind of like. And what this is doing is it's actually doing pitch detection, and I'll talk about that later. But then after it does pitch detection, it just plots a certain number of periods of the detected pitch just in the time domain. So it's like an oscilloscope. And you can, it kind of inspires textured playing. I'm not sure what the utility of it is, but I do really like this mode. And then this is a tuner, and it's kind of ironic, but the tuner is one of the least good features in this. Let me shut up, and then it'll probably work better. So So it kind of works, but I wouldn't recommend relying on it too much because the sample rate I'm using is like 10 kilohertz, which if you use like a smartphone app, that's going to be 44 kilohertz. It's just a lot more accurate. And I really wasn't able to push the Raspberry Pi Pico beyond 10 kilohertz. I tried a bunch of stuff, but it didn't work. And then okay, back to pitch. So those are the modes, and I think I'll probably just scroll through some of the code and point out some things that are interesting. And yeah, here's the code. It's on GitHub, and it'll be linked in the description. It's just a really long INO file. It's based on this earlier version, which was for Windows console, and it sort of looked like this. I was just printing characters to the console, and this had all of these different files in it. One for audio and one for chords and so on. But with the Arduino IDE, it's a lot more convenient to just have one long file. So I kind of just copied and pasted in the functions that I needed. So I'll just kind of skim over it quickly and point out any things that are interesting and have to do with audio or music. So over here, we're kind of defining our audio parameters. I'm using a sample rate of 10 kilohertz because I tried and I wasn't able to push it further. I think that's about as fast as the Raspberry Pi Pico can do. And I'm using this Arduino FFT library, as well as, of course, the library for the display. I did try to write some code to actually put bytes of data onto the display, but it's incredibly complicated. It's like some kind of puzzle, and so I decided to just use the library. So after that, we have this. So this is how chords are represented, and pitches are represented. Notes or pitches are represented with, by numbers like this. So 1 is A, 2 is A sharp, 3 is B, and so on. And I'm not dealing with flats at all or the distinction between sharps and flats. I'm just using like a chromatic system where you have naturals and sharps. So this is how chords are defined, and so you have the number of notes, and then you have an actual array where you store these pitch numbers for each chord tone, and then you have a character string for the name of the chord. And then there's a function to check whether a chord contains certain notes, and that's going to be used to actually look up what chord is currently being played. Then we come to this class audio cue, and this is interesting. I had done this for the console version, and I'm really happy that I used the Raspberry Pi Pico for this project because it turned out to be a good match, because although it doesn't have a sound card, it is dual core. And what I was able to do was just implement a sound card on core 2. So I didn't have to change much. And the audio cue is part of that, because what happens is core 2 puts audio data into the queue, and then core 1 reads it from the queue and does the analysis. And then this is a print text function from the examples for the display library, and I don't understand it. It's some kind of low level thing. But this is a show graph function for the piano roll mode and the kind of pitch mode, and the oscilloscope as well. And I wrote this, and essentially what it does is it takes an integer array of data, which in this case is going to be 32 integers, and then for each value, if it's between 1 and 8, it chooses to print something on that column. So the 20th entry in data would be printed to the 20th column on the screen, and so on. And how it's printed is based on these different things. So I have this one version here, which is just a histogram. So you see, as the value goes up, you just have more and more LEDs coming on over there. And then this is the piano roll version, where you kind of have a little bit of the graph, a little bit of a graph in the beginning, and then towards the end you just have these three LEDs at the bottom lighting up. And then these are the other versions, and they use some kind of binary stuff, tricks. So here, this is conversion between spectral index and frequency. So this has to do with FFT len. This, well, what is it? This literal, and that is going to affect how each frequency is interpreted. So essentially, if you're looking for 2 hertz, then you would look for a certain element in the spectral array, right? And which one you look at is determined by these frequencies. And then this one is one of the more interesting, but also kind of mathematical and dry functions. It's continued fractions, recursive continued fractions, to find the fundamental that corresponds to a set of harmonics. Because with a guitar string, what you have is that you have all of these different vibrational modes, and they're all going to be active to some extent. And you have to try and figure out what the fundamental pitch of the string is. And so this does that. It doesn't do it amazingly well, but it does work generally. And then this is for finding the peak. So before you can actually do the continued fractions, you need to figure out where the peaks are in the spectrum. So this is a peak detection algorithm that kind of compares the value with the moving average and does things that way. Then there's detect pitch, which uses those 2 functions to find pitch. These is all sorts of functions. Let's see, was there something? Yeah, so this writes the name of a pitch, So all of these functions are kind of useful. And then here, so this is kind of how the chord part of things works. I have this array A root chords. It's an array of chords, and I can I had never written an array of structures like this before, but I quite like it. And you can see how the chords work. So you have 2 notes, and they are the first and the 8th note. So you're looking at, from 1 to 12. So you're looking at A, and then whatever is 8, that's going to be A, B, C, D, E, and E, because it's a 5th. Anyway, so that's a power chord, that's a minor chord, that's a major chord, and so on. So you have all of these chord types. And in theory, you should be able to add more, although it seemed to be misbehaving with like 12 chords, but not misbehaving with 13 and stuff. So there might be some kind of bug there. Then what I'm doing here is I'm just taking those A root chords, and then I'm transposing them up by different amounts. And that way I have a complete dictionary of all chords that could be played, obviously excluding enharmonic equivalents, which are just spelled sharp always. So this is more functions. Now this one, notes visualizer, this is essentially what I explained in the previous video. So if you want to know how this works, you can go and check that out. And then this is the actual guitar tuner. And what this does is it does pitch detection, and then it has to display a string with the letter, as far into the string as you are sharp or flat, essentially. And so I'm printing spaces, and then at a certain point, I print the pitch name. And then the chord guesser, so I probably should talk about how this works. And how it works is similar to the notes visualizer. I'm kind of binning frequencies into different notes. In the case of the notes visualizer, I'm using 32 bins because there are 32 columns on the screen. With chord guesser, I'm using 12 bins. And so I'm getting how much of each note is in the sound. Then when I do that, I figure out, okay, what are the notes that are actually probably being played by an instrument and what are the ones that are not. And you do this by sorting and seeing if the first few in the sorted array are a lot greater than the others. So I have a threshold for that somewhere. And then once you have that, you go through all kinds of chords to figure out, your chord dictionary to see which one has matching notes. And then you try to figure out if out of all of the ones that have matching notes, there are some that are smaller than others or have the correct root note and things like that. So there's kind of a process of elimination there. This is the oscilloscope mode. And again, this is just doing pitch detection and then plotting the actual time series onto the screen. So this is the sound card essentially on Core 2, and how it works is you have a buffer of audio and you have a write pointer to where in that buffer you're writing your current sample, and then you have two variables to store current time and previous time, and this is going to be in microseconds because we're using this function micros. And what micros does is it just has a counter that goes up every microsecond, and then at some point it resets to 0. So what we're doing is we're constantly checking the time, and then if the time is correct based on the sample rate that we choose, then we read a new value and put it into the buffer and update the time. And then once in a while, what's going to happen is that your buffer is going to fill up. So this is your buffer size. So if your write pointer increments beyond that, that means your buffer is full. And so then what you do is you send the audio that you have currently to the audio queue and clear the buffer. So that's how a sound card works. And now you have this function to flash a message for the animations between modes. This is core 1. So this is the kind of main core which is going to be doing everything other than audio. It's controlling the screen, and it's also doing FFT and all of these different visualizer functions and such. And what it's doing is there's an integer called mode, and every time the button is pressed, it just toggles through the mode, and at the point that the button is pressed, it flashes a message, and after that it gets data from the audio queue, does the FFT, and then does whatever it's supposed to based on the mode. So yeah, that's how this works. Since it's just a single file and a few components that are plug and play, I think this could be a pretty fun beginner project if you like the results. So, and if you do build it, I would love to see what you come up with. And you can, it's easy to customize because you can. So if you go into the show graph, you can change the animation of how this works, and then wait, let me go down here. So you see the mode, we have 3 different chord guesser modes, and this is the number of notes. So when I put 2, it's only going to look for power chords. So it's going to tell you the bass note. When you put 3, it's going to look for triads, and 4 is going to look for more, and so on. So you can actually change what modes there are or aren't. You just need to update this. So let's see, there's a literal here called num modes. So you can put more modes in, or take out the ones you don't like.